research topic, both within the database and the algorithm community. And then the plan is at 2 o'clock, we're going to drive a small group thing. So that's the plan for today. So without further ado, Mahmoud is going to sort of give the introductory talk on relational algorithms.
Good morning, everyone. So the plan for us today to discuss relational algorithms, which is on the boundary between relational databases and algorithms, and some machine learning, depending on what kind of algorithms we're talking about. So the plan is for me this morning to start by giving you relational algorithms from the perspective of the relational database community, and later Kirk is going to present the algorithms community perspective. Yeah, special thanks to Dan Oltiano for providing many helpful suggestions for material for the slides, and to Wolfgang for volunteering to proofread the slides. Please feel free to interrupt at any time. This will work better if it is a group discussion. Okay, so here is the outline. We are going to start by taking a look at a brief definition of what we actually mean by relational algorithms. And then we will take a detour to review some technical tools that we need to develop some class of relational algorithms. In particular, the technical tools that we are going to need are basically some product queries. And then using those tools, we will see the one and only example that I'm going to present today of a relational algorithm, which is relational linear regression. Afterwards, we will see how far we can generalize this example, and we will end with some open-ended open problems. Okay, so what exactly do we mean by relational algorithms? It's a little bit under-defined term, but here is the high-level picture. The input to a relational algorithm is basically relational data, and the algorithm is typically meant to utilize the relational structure in order to achieve either a better performance in terms of space and time, or better results in terms of like accuracy, if this is, let's say, a machine learning task, depending on the problem at hand, or both. And in some cases, the output also of the algorithm can be represented relationally as relational data. So here is one example. Suppose that we are given this database join query. And for those of you in the audience who are not from the database community, let me review quickly what do we mean by actually a join query. So over here, we have a query with 4 variables, x1, x2, x3, y, and 3 binary tables. Every table basically lists potential assignments for its variables. So this is the table R, S, T. And the output of the join query is basically a table with 4 columns listing all possible assignments of the variables that satisfy this conjunction. So this is basically what we mean by a join query. And in a relational setup, the setup that is interesting to us for relational algorithms, the input is typically the query along with the input tables. Our targeted output is not exactly to compute the join itself. Instead, we are asked to compute something that depends on the join. This is basically the general idea. We want to compute something that depends on the join without computing the join explicitly, or at least trying not to. And what exactly this something that we want to compute could be? There's something that we are asked to compute. It could be something that is low level. For example, we could be asked to compute some aggregation over the table Q. For example, we could be asked to compute the summation of y squared over all rows in the table Q. Now, a non-relational algorithm would basically compute Q in full and then go over the last column y and sum away y squared. But this would take time. In the worst case, the multiplication of the sizes of R and T, because the Q itself is basically a subset of the Cartesian product of R and T. Now, instead, a relational algorithm can basically do this in a smarter way, where we can basically push the sum inside the join query. In particular, here, for every fixed x3, we can start by summing away y squared for this x3. and the result would be just a function from x3 to a number, which is basically this expression over here, which we can do in linear time in the size of t. After we do that, now for every fixed x2, we can go over x3s and sum away this function that we just computed. And now this new function can also be computed in time linear in the size of s, assuming we already computed the first function. And finally, we go over x1, x2 in R and compute the summation of the previous function. And everything will take time linear in the input size, modulo a log factor. So this is basically the simplest example of a relational aggregation algorithm, where we want to aggregate relationally by pushing the aggregate inside the query. A more advanced example.
Why is the one algorithm called relational and the other not?
Like this is not relational in the sense that the aggregation is completely oblivious to the join query. We computed the full join query before we did the aggregation. So the aggregation algorithm itself is not really aware of the relational structure of a queue. It's just taking a queue as a black box.
I bet some databases actually run that query, right? If you look at to optimize it sometimes.
You mean non-relationally? Yeah, it can happen.
You tried something like that with a simple like sorting and all, and they usually just compute the whole join first and then apply whatever operator afterwards. Even good commercial engines.
Yeah.
Not really.
I was about to say, thanks. Yeah. So this is so sort of the simplest relational algorithm task. Alternatively, there are some higher level computations that we might ask to perform relationally. So for example, we could be asked to train some machine learning model on Q using the table Q as some training data. So for example, we could be asked to train on a Q so that we can predict Y based on x1, x2, x3. And similarly, a non-relational algorithm would actually start by explicitly materializing a Q as a giant matrix, and then run a machine learning algorithm on a Q, where Q is now as a black box. The machine learning algorithm has no access to the query or what exactly does the table Q represent. It's just one big matrix. We already destroyed the structure of the data by converting into one big matrix, basically. Instead, what we are aiming for here in this talk is to operate directly on the input tables RST, which are potentially much smaller, asymptotically smaller than Q. In particular, we want to develop some sort of a machine learning algorithm that can run directly on those input tables. Or said otherwise, we want to push the machine learning inside the query. Just like in the previous case, in the previous example, we pushed the aggregate inside the query. So that's basically what we are hoping to achieve. Now, let's take a detour to review some technical tools that we are going to need to develop some class of relational algorithms. And the technical tools that we are going to need are basically what we call sum product queries. The reason we are going to need them is that many relational algorithms, at least some class of relational algorithms that we are going to discuss, can be described as a series of solving sum product queries. And in general, sum product queries are a universal language to express problems in several domains, including databases, linear algebra, constraint satisfaction, logic, PGMs, and etc. So it is an important topic on its own. But for the purpose of this talk, we are going to need it specifically to develop some relational algorithms. So what exactly do we mean by a sum product query? To specify a sum product query, the first thing that we need to specify is basically a commutative semi-ring, which consists basically of a domain, some binary operator that represents addition, a binary operator that represents multiplication, an additive identity 0, a multiplicative identity. And we also need some properties. We need the annihilation by 0 property. And most importantly, the most distinctive property of semi-rings is basically the distributive property, where multiplication distributes over addition in a semi-ring. So assuming that we have fixed a semi-ring, so how do we actually specify a sum product query? A sum product query consists of a variable set x. We need to fix some set of variables. And we also need to specify subsets of x, m subsets of x. So each one of these x1 up to xm is a subset of x. And each one of those subsets, let's take x1, has an associated function, psi1 x1, which is a function from the domain of those variables x1 into D, where D is the domain of the semi-ring. In addition, we also need another subset y of x, subset of variables. And our target is basically to compute a function from the variables y to D, the domain of the semi-ring. And this function is specifically defined as follows. We basically take the product of these functions, psi1 up to psi m, and then we take a summation over all variables x that are not in y in the output. And when we take this summation, we are left with a function over the variables y, a function from the domain of those variables into D. Now, this might sound a bit too abstract, but I promise this is actually the only abstract slide that I have. From this point on, everything will just be examples. So let me demystify this a bit by taking an example. Consider this example sum product query. Over here, we have basically 4 variables, a, b, c, d, and we have 3 functions, psi1, psi2, psi3. We are multiplying them together and summing over bc, and the output is a function over ad. Now, what exactly does this sum product query represent? It depends on what semi-ring we want to choose and what functions, psi1, psi2, psi3, we want to choose. So, for example, we can use this sum product query to encode the problem of detecting detecting in a graph E which pair of vertices A and D have a 3 path that goes from A to D. In order to encode this problem using this SPQ, the functions psi1 AB becomes the edge relation AB, which basically returns true if the vertices A and B have an edge and false otherwise. The product of the semi-ring becomes the and the summation becomes basically the or the exists. And now this query returns whether A and D have a 3 path from A to D. And what we used over here is basically the Boolean semi-ring. Alternatively, we could have used the exact same sum product query to count the number of paths from A to D. And for that purpose, we need to use a different semi-ring. We need to use the semi-ring of natural numbers, where now for the function psi1 AB, we need to use an indicator function of EAB, which basically returns 1 if there's an edge from A to B and 0 otherwise. And now the product of the semi-ring becomes the numeric multiplication. The summation of the semi-ring becomes the numeric summation. And now Q2AD is a function that returns the number of 3 paths from A to D. Alternatively, we could also use the same the same SPQ to ask what is the shortest path between every pair of vertices A and D. And for that purpose, the functions psi1 becomes the weight, the length of the edge AB, and instead of the product of the semi-ring, we use plus, and instead of the summation, we use min. And now we are computing shortest paths. Alternatively, we could also use the same SPQ to encode matrix multiplication, where now we use psi1, psi2, psi3 to encode matrices. We multiply them and sum over BC, and the result is basically a matrix that represents the product of these matrices. So the beauty of the sum product abstraction is that no matter what is the domain that we are talking about, whether it's graphs or matrix multiplication, we can always solve these queries in the exact same way using the semi-ring abstraction, using nothing other than the semi-ring properties. Here, yes.
Can you go to the previous matrix? So does this mean the matrix multiplication that M1 of AB returns a matrix? Or is that the entry? Or is it the value of the entry of the matrix?
This is just an entry. So M1, AB here, AB are the 2 indices of the matrix, IJ, and M1 is the value.
Okay.
Yeah, this would have been probably easier to see if we replaced A, B, C, D with I, J, K.
So, but then the semi-ring is the natural number, so.
Yes.
Okay.
Or real numbers. So let's take a look at a slightly more interesting example. Suppose that we are given now this query, this join query where RS and T are relations. It's basically a three-path query. And let's say our target is to compute the minimum L1 norm among all tuples x1, x2, x3, x4. And when I say L1 norm, we're basically talking about the summation of the absolute values of x1, x2, x3, x4. So we want to go through all these tuples, sum their absolute values, and then pick the value with the minimum value among all tuples in a queue. So how can we encode such a computation as a sum product query? Naturally, since we're talking about an L1 norm, which is a summation and a minimum, we should probably be using the min plus semi-ring. So we have to define some functions, psi r x1, x2, plus psi x, x2, x3, plus psi t, and we need to take the minimum. But now the question is, how do we actually define these functions, psi r, psi s, psi t, to achieve what we want? There are actually several options. One of them is this. We can define psi r to be the summation of the absolute values of x1 and x2 if x1, x2 is in R and infinity otherwise. Why did we choose infinity? Because it is the identity of the min operator, which is the addition of the semi-ring. So here we shouldn't really be using 0. We should be using infinity. Now we can define psi s a bit asymmetrically, where we only take the absolute value of x3 if x2, x3 is in S, and psi2 similarly. And now let's see what happens. For any tuple x1, x2, x3, if it does not satisfy this conjunction, then basically it means it does not satisfy at least one of those atoms, which basically means that one of these terms will be infinity, which means their sum will be infinity as well, which means it is not really going to interact with the min. However, for a tuple x1, x2, x3, x4 that satisfies this conjunction, we are basically going to get the absolute value of x1 plus x2 plus x3 plus x4. And we are minimizing over all x1, x2, x3, x4. So as a sum product query, this does indeed compute what we specified over here.
So obviously, you could have made a different choice in psi, r, s, and t.
Yes.
Associate them in a different way.
Yes.
What kind of framework would allow one to prove that those two queries with two different choices of such are actually what they want?
Like given a specific choice, we can actually prove that it is equivalent by basically considering tuples x1, x2, basically combinations of variables that satisfy this conjunction and take the product of all the values that we have. But it is, in some cases, it is actually interesting to try to see like the symmetry between these options, because it's not necessarily the case that you will get the same performance if you use any of those options. In fact, this is also an issue that we have in implementation.
So there's an optimization that you want to both justify somehow, but then you want to apply it creatively.
Yeah. Like in our implementation at Relational for some product queries, we do have a heuristic to try to construct these functions where we want to establish a mapping like this that can be as helpful as possible to us. Okay, so now that we have agreed what SPQs look like, so now we are going to start discussing how to actually solve SPQs. And apologies here to the database community who are already bored with the triangle query, because unfortunately I'm going to use the triangle query. But then remember that not all our audience comes from the database community, and our target here is to join our boredom with the algorithms community as well.
Join bored.
Oh.
And optimizing.
Yeah. Okay, so let's take this SPQ, over some semi-ring that we don't even need to specify. That's the beauty of the SPQ abstraction. So over here, we have 3 variables and 3 functions, and we are summing away over yz to compute a function over x. So how can we compute this using a join algorithm? It turns out we can actually reduce the problem of solving this query into solving a database join query, where we construct 3 relations, R, S, and T, take their join, where these relations are specifically defined as follows. R is basically the set of tuples xy for which psi1 xy is not 0. And by 0 here, I mean the additive identity of the semi-ring. And how does that exactly work? So for any tuple xyz that does not satisfy this conjunction, it basically means that it does not satisfy at least one of these 3 atoms, which basically means one of these psi's is going to be 0, which basically means this product is going to be 0. So for any tuple xyz that does not satisfy the conjunction, its contribution to this product is going to be 0, and therefore its contribution to the summation will also be 0. So we can ignore it. So we can only focus on tuples xyz that satisfy this join. This is basically the idea, why we can reduce this into a join query. And now, once we solve this join query, we can list tuples xyz that satisfy the join. For each one of those tuples, compute this product, and then sum away the y and z to get our target function. And we can do this using either a worst-case optimal join algorithm or some beyond worst-case optimal join algorithm. If you need more information or background about worst-case optimal join algorithms, the Hung actually in the bootcamp of this program about a month ago gave a couple of nice tutorials. And just a quick review for how do we measure the runtime of a worst-case optimal join algorithms, because we are going to need this later. The runtime of a worst-case optimal join algorithm is described in terms of a fractional edge covers. So a fractional edge cover is basically coefficients, assignment of coefficients that are associated with every relation in the query. So the relation R has a coefficient psi R, and these coefficients are non-negative numbers. Fractional edge cover is valid if every variable is receiving a total of coefficients from its adjacent relations that are at least 1. So for example, here, if we assign a coefficient of every relation to be 1, then this variable will be receiving at least 1. This variable will be receiving at least 1. So this is a valid fractional edge cover. And to estimate the runtime of worst-case optimal join, we need actually the minimum fractional edge cover, the one that minimizes this summation, the sum of the coefficients. And this is what we call rho star, or the fractional edge cover number. And assuming that we have this number for a given query, the AGM bound basically says that the output size of the query is upper bounded by n to rho star, where n is the size of these relations in the sparse representation. And the runtime of a worst-case optimal join algorithm is upper bounded by n to rho star within an extra log factor. Now, how does this rho star look like? For a k-click, it actually looks pretty good because rho star is just k over 2 for a k-click. But for a k-path, it's actually pretty bad. It's also k over 2, but a k-path is actually much easier than k-click. So which basically means worst-case optimal joins might not be enough to solve SPQs efficiently, which leads us to our next idea. So now let's take this 3-path SPQ, where we have 4 variables, x, y, z, t, and 3 functions, and we are multiplying them and summing away x, y, z, t. So how can we solve this more efficiently than simply taking like rho star, the fractional edge cover, which in this case would have cost us an n squared time, because we need at least 2 of these relations to cover the variables. Now we can notice the following. Over here, we are taking a summation over t, but these 2 functions do not really involve t. So basically, using the semi-ring distributive property, we can pull these 2 functions outside the summation over t, so that the summation over t only wraps this function. Specifically, we can do this as follows. So we push the summation over t inside so that it's only over psi 3 using the distributive property of the semi-ring. And what we have over here, this expression now, is just a function over z that we can compute up front. And it can be computed in linear time in the size of psi3, or more specifically, the size of the sparse representation of psi3, or the number of non-zero entries in psi3. Now, once we compute this, we can plug it in back into phi. And now we have a query that no longer has a variable t explicitly. It only has variables x, y, z. This is basically what we mean by variable elimination. So we started from a query that is over x, y, z, t. And using this step, we created a query that is just over x, y, z. We eliminated a variable t. We can do this one more time, let's say, over variable z. So we can notice that psi1 does not really involve z. And this enables us to push the summation over z inside. And now we can compute a function over only y in time, which is linear in the size of the sparse representation of psi2. And now we are left with this query, which does not involve even z. So we eliminated two variables, and we are left with only x, y. And if you follow this strategy, you can basically solve this SPQ over any semi-ring in linear time, basically in the sizes of psi1, psi2, psi3. So now the question is, how far does this strategy generalize? So here is a more interesting query to test this idea. So in this query, I'm taking basically, we have overall 5 variables, A, B, C, D, E. And we also have 5 functions. I'm thinking here of R, S, T, U, W, not as database relations, but as functions to the domain of the semi-ring. We are summing away B, C, D, and E to get a function over A. And now the question is, which variable should we choose to eliminate, and what exactly is that going to cost us based on the variable that we choose to eliminate? So let's say we choose to eliminate D. If we choose to eliminate D, D is involved in 2 of these functions, W and T. So if we try to eliminate D, we will basically pull everything else outside of the summation over D, so that inside we only have T and W. But still, this elimination is going to compute this factor psi D, which is over BCE. It no longer has D because we are summing D away. But still, this is actually going to cost us quadratic time. But we might be able to do better. So let's try another variable. What happens if we try to eliminate E? If we try to eliminate E, there are only 2 factors, 2 input functions that basically involve E, U and W. So using the same logic, we basically get, to eliminate E, we will basically have to compute this expression, which computes a function of psi E. But even this is still quadratic. It takes time n squared. However, we can eliminate E a little bit smarter. In particular, in this expression, we can also include an extra factor, T prime CD. And this function, T prime CD, is just a 0-1 function that returns 1 whenever TBCD has at least 1 B value for which TBCD is non-zero. And you can argue that adding this function T prime in here is not really going to change the function phi, because T prime is always 0-1, and it can only be 0 by definition if T itself is 0. Therefore, plugging in T prime in here does not really change phi, and this is basically what enables us to pull off this trick. And now when we eliminate E, we have a triangle. Instead of just including those 2 relations, now we have this T prime, which is a spanning CD. And this is basically a triangle that we can now solve using a worst case optimal join algorithm to get n to the power of 1.5. So this is basically the strategy that we are going to use to solve SPQs. We are going to look for a variable to eliminate. When we eliminate it, we have to solve a smaller SPQ. In this case, this is the smaller SPQ that you have to solve for it to eliminate E. This SPQ, we call it psi E something. And to solve this SPQ, we are going to use a worst case optimal join algorithm. But we are also going to try to utilize as many projections as we can to drive down the fractional edge cover number that we are using to measure the runtime of the worst case optimal join algorithm. And now the question is, how do we measure the runtime for a strategy like this to solve some product queries? Yes?
Do you have some way to figure out which order would be better for eliminating the variables? How do you know? Do you have some method by which you know that you should eliminate E first because?
Yes. Yeah, so this is basically what I'm going to define here. So over here, we are going to define a notion which is the sum product query width, which basically a measure of the runtime for the best possible runtime over all variable elimination orders. And we have a result that basically reduces approximating the sum product query width to approximating the fractional hypertree width. And there are known algorithms to approximate the fractional hypertree width that we can use as a black box so that we can approximate the sum product query width. So if
Wait, sorry, it's the fractional tree width
yes,
with respect to the fractional cover of like just kind of like the basic LP for the problem is the fractional cover.
it's the fractional hypertree width, which is a bit more complicated than the fractional edge cover. And yeah, unfortunately, computing the fractional hypertree width itself is actually pretty difficult because it's not just a matter of linear program because we need to break down the query into all possible 3D compositions. But there is actually a polynomial time approximation algorithm for the fractional hypertree width that we here rely on to approximate also this notion of width.
Gotcha. Okay.
Yeah. So if we fix a variable order sigma, then in order to measure the runtime for this elimination process, we have to go through every variable in sigma and eliminate them one by one. In order to eliminate them, as we discussed in the previous slide, we have to solve some smaller SPQ that eliminates V. So I'm calling it here psi V, and it also depends on the elimination order. And in order to solve this query, we have to pay a cost, which is the fractional edge cover number rho star for this particular SPQ. So this expression over here measures the overall cost that we have to pay if we pick sigma as a variable elimination order. If we minimize overall sigma, this is basically what we define as the sum product query width.
Mahmoud, excuse me. Help me understand this. The expression inside the parentheses, if you go to your previous slide, you change the query by adding the atom, T prime.
Yes.
How do you account for this? How do you, what are you allowed to add? I mean, how do you figure this out in the elimination cost? Because you could have chosen something different, right?
Yeah, so basically, the way we describe it is as follows. So in order to eliminate, let's say, a variable E, we have to define a new function. We have to solve an SPQ over CED, because E is involved directly with C and D are neighbors of E in this hypergraph. Now, the quantity rho star that I'm using here is basically the fractional edge cover number of this subset of the hypergraph, CD and E. And
Mahmoud, if I understand correctly, you're going to include not just a projection of T on T, but also the projection on S, which didn't help you, but you include everything that contains variables from your factor.
yes. Yeah, that's basically the definition of the fractional edge cover number of a subset of variables in a hypergraph. We are basically allowed to use hyper edges that are not directly included in the subset that we are interested in. And there is an algorithmic justification for this in the sense that we can indeed algorithmically utilize them, so we allow them. And this is indeed how the fractional hypertree width is defined. So for this query, it is indeed true that the fractional hypertree width, like as defined in the textbook, it should be 1.5. It shouldn't be n squared, or it shouldn't be 2. Yeah, so this sum product query width can be seen as a measure of the runtime. In particular, n to the sum order query width measures the runtime within an extra log factor and some factors that depend on the query size. Here, I'm just focusing on the data complexity. So n to sum order sum product query width is a measure of the runtime of this variable elimination strategy that I just described. So here are some special cases to think about this expression. This expression, sum product query width, is one for alpha acyclic queries without free variables. And it's also one for free connex queries, which Nofar told us about yesterday. For queries without free variables in general, it reduces back to the fractional hypertree width. And for more background about 3D compositions and width measure, I also invite you to watch Hank's tutorial in the bootcamp about a month ago. So in general, for queries with the free variables, it could be higher than the fractional hypertree width. And we will see a couple of examples.
Question for anyone. Is the variable elimination here, how does it relate to semi-joins and Yanakakis and stuff like that? It feels like a generalization.
So Yanakakis can be seen as a special case when we apply this variable elimination strategy on acyclic queries over the Boolean semi-ring.
Yeah, yeah. So this is a generalization of that.
Yes.
Yeah. Nice.
Okay. Yeah.
So if you have three variables, it's not clear, or is it still open the diff if you have three variables in general cases? Right?
Yeah, so free variables tend to increase the width. You can no longer talk about the fractional hyper. You can like the sum product query width could be higher than the fractional hypertree width, for the same reason that queries, even if they are acyclic but they are not free connex, you cannot do them in linear time. In fact, I have an example over here.
Is there a notion for this? In the same way that the fractional hypertree width is the projection-based notion that quantifies the bit that you would like to use. Is the notion for this width free variables? So
yeah. So the notion of this width with the free variables is, by definition, the sum product query width. So the fractional hypertree width does not really take free variables into consideration because it's just defined over a hypergraph. It is not defined over a query.
Is there a reason why you restrict to one elimination order here? So isn't submodular width roughly the same, but you can also split your tables and then use different elimination orders in different parts of your tables?
That's indeed true. So for the purpose of this talk, we just wanted to stick to like the basic thing that we need in order to get a rough idea regarding estimating sum product queries. So yeah, it is not really the state of the art. The submodular width can actually drive the runtime even further.
But it doesn't work for all semi-rings, right?
That is indeed true. Yeah. So for in general, for the submodular width only works for the Boolean semi-ring. For other semi-rings, we have a notion of sharp submodular width. Yes, it does work for other semi-rings in general, not just for counting. Yeah. Yeah. So this talk is not really meant to be like to give full background on width measures. It's just meant to give like a minimal subset that is needed for us to discuss our next relational algorithm.
Excuse me, Mahmoud, the relationship between this SPQ width and the fractional hypertree width, is it the same as between acyclic and free connex, so that you just add an artificial hyper edge with the free variables and then you determine a fractional hypertree decomposition?
Yes, you can think of it this way. Like the gap between those two in general, when we have a free vars, is just to account for the free connexity effect.
Okay.
Yeah, so if let's take, for example, this three-path query XYZW, where we are summing away everything. So what do you think the SPQ width should be this time? Yeah, it is actually 1. Now, suppose that we change it a little bit so that we are grouping by YZ. It's still a free connex, which basically means it's still 1. But now here is a more interesting case. So now let's take a two-path query, X, Y, Y, Z, but we are summing away Y. So this is not really free connex. And here we have to pay a price of 2. In particular, here we run in time n squared, like in the sparsity of R and S. This is basically sparse matrix multiplication. By the way, there are actually better results. So as I mentioned before, SPQ width is not really the state of the art. So it's for this sparse matrix multiplication, it's possible to do it in using a combinatorial algorithm in a better runtime, which is more output sensitive. But this is probably beyond the scope of this talk. If you want, if anyone is interested, I can tell you like afterwards in private.
Excuse me, but shouldn't it be 1.5? I mean, you throw in this artificial hyper edge, which consists of the output variables, then you have a triangle, and then it should be 1.5.
So this is exactly what I was just talking about. It's not exactly n to the power of 1.5. it is n times square root of the output size, the square root of the sparsity of Q3. This is exactly what I basically was referring to. So yeah, it is indeed possible to utilize the triangle query. Even though this is not a triangle, it is possible to utilize the time analysis for the triangle query to get runtime of n times square root of the output size, or the sparsity of the output. So it's basically the sparsity of the input times the square root of the sparsity of the output.
So this too is basically sort of like an outer product.
Yes, because in the worst case, we could have only one y value, and we have an outer product of x and z here. Now, what happens if we have a product of three matrices, R, S, T? Any guesses on the SPQ width?
2.
Yeah, it should be 2. It doesn't really increase because we basically do these eliminations one at a time. We eliminate z, basically multiplying R, S, T, eliminate y. So it doesn't really increase the width. So with that, we have all the background that we need on SPQs, so that we are now ready to get into our example of a relational algorithm, which is going to be linear regression applied relationally. So let me give you a few references. So what I'm going to describe right now, the method that I'm going to describe is based actually on this paper, which is originally POTS 18 paper. Dan Oltiano's group at Zurich, previously at Oxford, has a series of systems papers pushing the boundaries of relational algorithms to cover more and more machine learning models. In fact, Dan's student, Max Schleich, who is currently at Relational AI, did his entire PhD on this topic. And also, Arun Kumar's group at UC San Diego has a parallel research thread on this topic. And we at Relational AI have been involved with many of these papers spearheaded by Hang. So basically, I have 2 points to make here on this slide. First, I want to give you some references, but also I wanted to point out that there are like many experts working in this area, and I'm actually very far from being the best expert to give this talk. But I happen to be the cheapest one around, so this is why I'm talking to you today. Yeah. Welcome to our budget program. Okay, so how does relational linear regression look like? What is exactly the setup? In the relational setup for linear regression, our training data is not given explicitly. Instead, it's given to us as a join query. In particular, here we are given these three tables, where the first table maps a pair of item and a city to the sales of this item in this city. We have another table that lists lists pairs of item and price. I'm not assuming here that there is a functional dependency from item to price, because the same item could have multiple prices on multiple days or multiple places. And we also have another table that maps a city to its country. And our training data is basically the join of those, comes from the join of those tables into one big table, Q, which has 5 columns. So this query is what we call the feature extraction query, in the sense that it basically extracts the features that we want to use for training. And our target in relational linear regression, so in this example, let's say, is to learn how to predict sales based on these 4 features.
Remy has a question. Let me. He's saying that you said variable elimination generalizes Yarnakakis, but for acyclic full conjunctive queries, Yarnakakis runs in linear time. Yet variable elimination would be the same as worst case optimal join, since there is nothing to eliminate.
Yeah, that's true. So I was thinking of Yarnakakis without free variables. Yeah. So what we want here is basically to predict sales based on item, price, city, and country. And we are going to use basically linear regression with square loss, which I'm going to review shortly. So in a traditional machine learning setup, which what we call structure agnostic or non-relational, the first step that we do is basically to compute the join queue to materialize this big table, which is potentially much larger than the input tables themselves. And not only that, in a traditional machine learning setup, we also have to one-hot encode it. So remember that item, city, and country are categorical features whose numerical values don't really have any inherent meaning. So it doesn't really make any sense to use like some numeric value for code in our learning model. Instead, we have to go one-hot encode a vector of items so that, let's say, a code is encoded as 1, 0. Shoes will be encoded as 0, 1. And we have to do this for also cities and countries. So we get this table, one-hot coded table, which is potentially much larger. And our model for relational regression basically means we want to find a vector theta whose dimensionality is the same as these features, such that the inner product of this vector with every row of this table is as close as possible to our target sales. Let me give you a more precise definition. So here in our training data, these in every row in the training data, this is basically the vector x of features, and this is our target y. And basically, our target is to find the theta that minimizes the following expression. Over here, we have theta times x, this inner product, is our prediction for a given combination of input features x using our parameter vector theta. And our target that we are trying to aim for to get the best theta that as close as possible to it is basically y. So we are trying to minimize. So we basically take the error, which is basically the difference between our prediction versus the true y, and we square the difference, and we sum over all pairs in our training data. So this term over here captures the least squares loss, the error in like our prediction versus the true values that we are trying to predict. And over here, we will have another term that is basically going to penalize large thetas, so that it basically can reduce overfitting. So this is what a typical objective function for linear regression with least squares and an L2 regularizer look like. And like for the purpose of this talk, we will think of batch gradient descent that is being used to compute the optimal theta, where we iteratively improve our theta by applying this over and over. So what exactly is wrong with the traditional machine learning that is basically structure agnostic in a relational setup? There are actually several issues. One of them is that we have a twofold size blow-up in our training data. In particular, we start from these input tables, S, P, and C. We compute their join, which is potentially asymptotically larger, and we have to one-hot encode it, which is even potentially much larger than Q itself. So we have a twofold size blow-up. And we are also destroying the data structure, because once we compute the matrix data and feed it to the machine learning algorithm, the machine learning algorithm has no access to what these features represent or where they came from. We will lose access, basically, the machine learning algorithm will lose access to the join dependencies and function dependencies in the data, and it will have to do some extra work to rediscover those dependencies. Moreover, there will be some expensive data move between the database into the machine learning. We'll have to export our data and then train the model in the machine learning and then import the model back into the database. And there are also other issues, for example, related to high maintenance cost. Now, suppose that after we train our model, there is some insertion, let's say, into the table S. And our target is to figure out how this affects our learned model. It's really hard in the non-relational setup to compute how this affects our trained model without recomputing everything from scratch. So instead, in relational machine learning, our target is basically to address some of those concerns. Here is the outline of one potential approach that I'm going to describe here in detail, how we apply it for this particular example. The first step is going to be, we will factor out computations that are independent from theta. Now, remember that theta is going to change when we apply batch gradient descent. So computations that are independent from theta, we can compute them only once at the beginning. And when we apply batch gradient descent, they don't really have to be updated anymore. Step 2 is going to be encoding these computations as sum product queries, which is why I wasted half an hour recalling sum product queries. And there are actually two benefits to encoding them as sum product queries. We already have efficient algorithms to solve sum product queries that will factor the computation over the input table so that we don't have to do the join. And I'm going to give you some exactly how this works out in this example. Even better, when we have like a bunch of SPQs, as we will see shortly, many of these SPQs are going to share some computation. So we don't really have to solve them independently. We can reuse some components of these SPQs to help one another, reducing the overall cost. So let's substantiate now each one of these steps one at a time. So what exactly do we mean by factoring out the theta independent computations? This is basically our objective function in terms of theta. Our target is to basically to pull theta out as much as possible, or said otherwise, we want to push this summation over our training data inside as much as possible. If we expand this square and push the summation inside, you will basically get these three summations. Over here, we have basically a matrix that is sandwiched between two thetas. And this matrix turns out to be what we call the covariance matrix of the data. In particular, it's a summation over every feature vector x and target y of our training data, a summation of the outer product of x with itself. So this is a square matrix whose dimensionality is basically number of features times number of features in one-hot encoding. We have over here like a similar vector, which is basically a summation of x times y for every input feature x and its corresponding target y. And over here, there is another scalar, which is a summation of y squared. So basically, these three quantities, sigma, c, and s, we can compute them only once. And we don't really have to touch them anymore during gradient descent. And they depend on the data. They are the only thing that depends on the data. Theta itself does not really depend on the data. So this is basically what we are hoping to achieve. And the same actually applies for the gradient. When we compute the gradient is directly written in terms of sigma and c. So we are going to start by computing these terms, sigma, c, and s separately. And then let's just focus on sigma. Recall that this is basically what our training data looks like. So these columns without cells, these are x, our input feature, the vector x in the previous slide. And this is y, our target. Now imagine a square matrix which has the same number of rows and columns, where we basically go through every row in this matrix and take its outer product with itself. Now, the matrix sigma that I described in the previous slide is basically this portion of the matrix, where we go over only this part and take its outer product with itself and sum over all rows in the training data. This matrix is also symmetric. So the vector c that I described on the previous slide can be seen either as this portion or as this portion. And the scalar s is right here in the corner. And if we look more closely, so now let's focus on sigma itself. How are we going to compute? Yes?
About 5 more minutes, just to give you.
Yes, yes. Hopefully it will be enough time. Yeah. So the matrix sigma can be broken down into smaller parts. Over here, I'm calling them so for item, we are going to have a block inside sigma, which is sigma item item. Now, sigma item item is one part of the big matrix sigma, one block, and it results by going through each row here and looking only at the one hot coded vector item and taking its outer product with itself and summing over all rows. When we do this, notice that sigma item item is a diagonal matrix. And similarly over here, so over here we will have another block of sigma called sigma item city, which results by going through these rows one by one and taking the outer product of item with city. And as a result, we are going to get a 0-1 matrix, not a 0-1 matrix. When we do a summation, it will no longer be 0-1, but it will have it will be a 2x3 matrix. So we will have to compute all of these sub matrices or blocks in order to compute sigma overall. So how are we going to encode these as sum product queries? Remember that this is basically our query, our join query that computes Q. Sigma item is a diagonal matrix. It is enough for us to compute only the diagonal entries. We don't have to compute the full matrix. If you follow through the definition from the previous slide, sigma item basically results from going through all tuples, item, city, country, sales in a queue, and grouping them by item and counting how many tuples we have per item. So basically, in order to compute this entry, we have to go over every item and count how many tuples, price, city, country, sales are in queue, matching this particular item. We can express this as the following SPQ, where over here, we are using indicator functions, 1s item city sales. So this indicator function returns 1 if the triple item city sales is in S and 0 otherwise. And over here, we have another indicator, 1p, 1c. We take their product. So their product is going to be 1 only when the tuple item price city country sales is in a queue. And we are doing a summation over price city country sales. So when we take this summation, we will basically count for every item the total number of tuples in a queue for this particular item. So this is the SPQ for item. There is a similar SPQ for item city. It's exactly the same thing. So over here, we didn't really change this conjunction, this product. However, over here, now we are grouping by item city. So for every pair item city, now our target is to count entries in a queue with this pair item city. Now, what happens if we consider, let's say, a continuous variable price, and let's say we want to look at sigma item price. For sigma item price, price is a continuous variable. So our target basically is to, for every item, to compute the summation of a price for all tuples in a queue that have this item. So for every item, we sum away price over all entries in a queue that have this item. And this also can be represented as an SPQ, like this. And if we have, if you are interested, let's say in sigma price, it's a similar SPQ, except that we are taking a price squared and summing away over all variables. So then the thing to remember here is that for every entry of sigma, there is an SPQ. These SPQs look very similar. They only differ in two aspects. They differ in potentially some variable here or some combination of variables that we are multiplying into these indicators. Over here, we have, let's say, price squared. Over here, we have nothing. And they also differ in their group by variables and which variables we are summing. Even better, so now once we construct these SPQs, we can use what we learned about solving SPQs to solve them efficiently. So if we take, let's say, this SPQ and applying variable elimination, we can basically factor this out into smaller SPQs. If we eliminate price first, we will discover that we have to compute this expression independently. If we eliminate country afterwards, we will discover that we have to compute this expression separately, and so on. So this entire SPQ can be actually solved in linear time in each one of the input tables if we compute each one of those sub-expressions separately using variable elimination. If you take another SPQ, there will be actually a similar variable elimination strategy where we will also discover that we have these sub-expressions to compute separately. So variable elimination helped us basically avoid computing this join. But even better, if you look at the result of variable elimination for those two different parts of sigma, you can notice that they share some expressions. So this expression, we only have to compute it once for both entries. And similarly for this expression. So basically, there are two benefits to variable elimination: avoiding the join and sharing computation among the different components of sigma.
Mahmoud?
Yes.
Isn't this conditional independence marginalization in graphical models, isn't it isomorphic to that?
Yes, yes. In fact, SPQs, like one possible application is solving PGMs by taking advantage of conditional independence.
Okay, thanks.
So overall, what did we gain by applying machine learning relationally? I will wrap up in a couple of minutes. I know I'm running a bit late. So one thing is that database relations serve as a sparse sensor representation out of the box. So like in the previous case, let's say, just because we encode these tables as SPQs in a database where these are represented in a sparse way, the output naturally is going to be a sparse matrix. We will never basically, let's say, materialize pairs item city for which there is no combination in the training data for this pair item city. So everything out of the box, when you implement it in a database, will turn out to be a sparse sensor. Moreover, when we encode these relationally and use a reliable database engine, we can utilize the query optimization. So for example, if we have good support for SPQ solving in our database, as we saw, we can utilize SPQ. Moreover, database query optimizers typically have many other optimizations. They can, for example, take advantage of integrity constraints. So for example, if we have functional dependency from city to country, a reasonable database optimizer would figure out that this summation, where we are summing away country over every city, is actually trivial because of the functional dependency. We can also utilize worst-case optimal join algorithms if our database supports worst-case optimal join algorithms. We will also get other benefits. So typically, databases support parallelization, and just because we encoded our machine learning algorithms as a series of database queries, we will get a distributed machine learning algorithm for free out of this. Even better, we can get free support for incremental machine learning, where basically just because we encoded everything as database queries, if these database queries are incrementally maintained, then our machine learning model is now incrementally maintained. After every insertion, let's say, into the input tables, our database is going to automatically maintain the SPQs, and by extension, the matrix sigma, and by extension, the model. Yeah, so let me wrap up here. I'm going to skip this part. By the way, the slides are available online. There is a Google Drive folder that Sudeepa created that contains basically slides for the entire program, including this workshop. So how far can we generalize this example? Out of the box, we can generalize it to polynomial regression factorization machines. If we allow for extra tricks, we can generalize it actually to a lot more models. You can support piecewise linear or polynomial functions, but then we will need to support SPQs with some linear inequalities in them. Kirk is going to tell us more about that. And we can also support SVMs, classification and regression trees, and a lot more once we support linear inequalities. But fundamentally, there are models, especially deep models, that are completely outside the scope of this approach. And the most natural open problem basically is to see how potentially we can support deep architecture, like deep neural network. In particular, like based on relational data, we can either think of designing a specific model structure that is tailored for the relational data structure that we have. As an analogy, for graphs, we do have graph neural networks. So for factorized data, do we know whether there is some notion of factorized neural networks that are pre-tailored to learn over factorized data? Wolfgang actually told me before the talk that apparently there's already some work in this direction that he has been working on. And if we don't want to tailor a model structure for the relational data, we can at least talk about restricting the model parameter space to take advantage of what we know about the relational data. So for example, can we impose some reasonable constraints on the model parameters, the weights, while still showing that thanks to the relational structure, we are not really going to lose anything in the precision, potentially speeding up gradient descent. I'm really sorry for going over time. I really appreciate your attention.
Given that we're well ordered, why don't we just take the coffee break, and I'm sure Mahmoud would be happy to chat with you about that.